Hey, welcome back to IT Clicked. Quick recap of where we are. We know that every computer follows the von Neumann blueprint: CPU, memory, storage, and input, output, all connected. And we know the CPU is the brain, it's where all the thinking happens. But we've been treating the CPU like a magic black box. We said the CPU processes things and moved on. Today we're opening that box. And I want to warn you, what's inside is both simpler and more mind-blowing than you'd expect. Simpler because the basic idea is incredibly straightforward. More mind-blowing because of what humans managed to build from that simple idea. Let's go. Let's start with the most basic question possible. What is a computer, at its very core? Here's the answer: a computer is a machine that works with electricity. But not in a complicated way. In the simplest way imaginable. Imagine a light switch. It has two states: on or off. That's it. A computer is, at its heart, billions of tiny switches. Each switch is either on or off. And that's literally it. That's the entire foundation. When a switch is on, we call it a 1. When it's off, we call it a 0. You've heard of binary, ones and zeros. That's all binary is. On and off. Yes and no. True and false. Everything your computer has ever done, every photo, every video, every message, every game, is just a massive pile of ones and zeros. Billions of tiny switches being flipped on and off, billions of times every second. Now, you might be wondering, okay, but how does a bunch of on-off switches add up to, watching Netflix? That's what this video is about. The first step is understanding something called a logic gate. A logic gate sounds technical, but the idea is incredibly simple. It's a tiny circuit, a tiny piece of electronics, that takes some switches as input and produces a result based on a rule. Let me give you a completely non-computer example first. Imagine you work at a theme park. Your job is to decide whether someone is allowed onto a roller coaster. And there are two rules. Rule 1, the person must be tall enough. Rule 2, the person must not have any health warnings. You only let them on if both conditions are true. Tall enough and no health warnings. If either one fails, they don't get on. That's exactly what an AND gate does. It looks at two inputs: are they both on? And only gives a 1 as output if both inputs are 1s. If either is a 0, the output is 0. Now imagine a different scenario. You're a security guard at a building that has two entrances. If either door opens, an alarm goes off. Just one is enough. That's an OR gate. Give me at least one on input, and the output is on. And then there's the NOT gate. The simplest one. One input, one output, and it just flips it. Give it a 1, it gives back a 0. Give it a 0, it gives back a 1. It's like a person who always disagrees with everything you say. And, or, not. 3 types of gates. 3 simple rules. And here's the part that blew my mind when I first learned it: from just these 3 types of gates, you can build literally everything a computer does. Every calculation. Every decision. Every piece of software ever written runs on combinations of these 3 simple gates. Let me show you how. Let's use logic gates to build something real. Let's build a machine that can add 2 numbers together. We'll start really small. Just adding single digits in binary, so just 1s and 0s. 0 plus 0 equals 0. Simple. 0 plus 1 equals 1. Fine. 1 plus 0 equals 1. Same thing. 1 plus 1 equals 2. But wait. In binary, we don't have the digit 2. Binary only has 1s and 0s. So 2 in binary is written as 1, 0. Like how in normal numbers, when you get to 10, you write a 1 and a 0. Same idea, just happens way earlier in binary. So 1 plus 1 doesn't just give us a result of 0, it also gives us a carry, a 1 that needs to go to the next column. Now watch this. Look at just the result digit. It's 0 when both inputs are the same. It's 1 when the inputs are different. That exact pattern is what an XOR gate does, it gives 1 only when the inputs are different. Look at just the carry digit. It's only 1 when both inputs are 1. That's what an AND gate does. So to add two single binary digits, you just need one XOR gate and one AND gate. That's it. Wire them up and you've got an adding machine. Now link 8 of these together and you can add numbers up to 255. Link 32 together and you can add numbers up to 4 billion. That's how the math unit in your CPU works. All of it, addition, subtraction, multiplication, comparison, built from tiny combinations of AND, OR, and NOT gates. Rules about on and off. Now let's talk about how these gates actually exist in the physical world. The answer is transistors. A transistor is a tiny electronic component with one job, act as a switch. Apply a small electrical signal to it and it allows current to flow, it's on. Remove the signal and current stops, it's off. An AND gate is just a few transistors wired together in a specific way. An OR gate, a different arrangement. A NOT gate, even simpler. Now here's where it gets crazy. In the early days of computing, transistors were about the size of your thumb. Then engineers figured out how to make them smaller. And smaller. And smaller. Today, the transistors in your phone or laptop are a few nanometers wide. What's a nanometer? 1/1000th of a meter. Your hair is about 100,000 nanometers wide. These transistors are so small that you could fit thousands of them inside a single human cell. And your iPhone has around 16 billion of them. 16 billion. Tiny switches. Each one either on or off. All of them working together. That little chip in your phone is one of the most complex objects ever built by humans. And its entire job is to flip tiny switches on and off, very fast. Alright. Now that we understand the basic building blocks, let's zoom in on what's actually inside a CPU and how it all fits together. A CPU has three main parts. Think of them like the three things a very competent office worker needs to do their job. The first is a calculator. The second is a notepad. The third is a manager. Let's go through each one. The calculator inside the CPU is called the ALU. That stands for Arithmetic Logic Unit, but don't worry about the name, just think calculator. The ALU is where numbers go to be worked on. You give it two numbers and an instruction, add these, subtract these, compare these, and it gives you back a result. When Spotify is adjusting the volume of a song, the ALU is doing that math. When a game is checking whether your character's health has hit 0, the ALU is doing that comparison. When your browser is figuring out how to lay out a web page, the ALU is handling the calculations. Everything that feels like thinking in a computer is ultimately the ALU crunching numbers according to the rules built from logic gates. And it's fast. Unimaginably fast. A modern CPU can perform billions of these calculations every second. Not millions. Billions. The notepad is called registers. Here's the thing about the ALU, it can calculate stuff, but it needs somewhere to put the numbers while it's working. It can't just reach all the way into your computer's memory every single time it needs a number. That would be too slow. Imagine you're cooking a recipe. The full recipe is in a book on the shelf across the room. But while you're standing at the stove, you don't want to run to the shelf every time you need to remember the next step. Instead, you jot down the key things you need right now on a small notepad right next to you. Registers are that notepad. They're tiny, a modern CPU only has around 16 to 32 registers. And each one can only hold a single number. But they're incredibly fast, the CPU can read from or write to a register almost instantly. When the CPU wants to add 5 and 3, it writes 5 into one register, writes 3 into another register, tells the ALU to add them, and the result, 8, goes into a third register. All of this happens without touching the main memory at all. Some registers have special jobs. There's one that always keeps track of which instruction the CPU should do next, like a finger pointing to the current line in a recipe. There's one that holds whatever instruction is currently being executed. And there are several general ones where the CPU just parks numbers it's actively working with. The whole system is designed around one thing: speed. Keep the most immediate stuff as close to the calculator as possible, so the calculator never has to wait. The manager is called the control unit. The control unit doesn't do any calculating itself. It doesn't store anything. Its entire job is to tell everything else what to do and when to do it. Remember the fetch-decode-execute cycle? The control unit runs that loop. It goes to memory, grabs the next instruction, brings it back. That's fetch. It looks at the instruction and figures out what it means. Is this an addition? A comparison? A move? That's decode. It then sends signals to the right parts of the CPU. That's execute. Then it immediately goes back to fetch the next instruction. Over and over, billions of times a second. The control unit is the reason all those separate parts, the ALU, the registers, the memory connections, work together as a coordinated machine instead of just sitting there doing nothing. Now let's talk about speed. Because how fast is fast, actually? Every CPU has something called a clock. Not like a wall clock, it's a tiny crystal inside the chip that vibrates at an extremely precise rate. Every vibration sends a pulse through the chip. And on every pulse, the CPU takes one step forward in its work. You've probably seen the term gigahertz when looking at computer specs. Like 3.5 gigahertz processor. That means the clock in that chip pulses 3.5 billion times per second. 3.5 billion pulses per second. Each pulse is like a heartbeat of the CPU. And on each heartbeat, something happens. An instruction gets fetched. A number gets added. A result gets stored. More gigahertz generally means more work done per second. That's why a faster processor often means a snappier computer. But there's a catch. The faster you run the clock, the hotter the chip gets. Push it too far and the chip starts making mistakes or just burns out completely. That's what that fan in your laptop is for. That's why gaming computers have massive heat sinks and sometimes liquid cooling. The processor is running so fast it would literally overheat and destroy itself without something keeping it cool. Now let me tell you about one of the most clever tricks CPUs use to go even faster, without increasing the clock speed at all. It's called pipelining. Think about a laundromat with one person doing all the work. They take a load of laundry. They put it in the washing machine. They wait for it to finish. They put it in the dryer. They wait for it to finish. They fold it. They put it away. Then they start the next load. That's inefficient. The dryer sits idle while the washing machine runs. The washing machine sits idle while the dryer runs. A smarter approach: while load 1 is in the dryer, put load 2 in the washing machine. And while load 2 is washing and load 1 is drying, start folding load 0 that's already done. Multiple loads, all at different stages, all moving forward at the same time. CPUs do exactly this with instructions. While instruction 3 is being executed, instruction 4 is being decoded, and instruction 5 is being fetched. They're all in the pipeline at the same time, just at different stages. A modern CPU's pipeline can have 15 to 20 stages. Which means at any moment, 15 to 20 instructions are in progress simultaneously at different points in their journey. This is one of the main reasons why modern CPUs are so absurdly fast, even without the clock speed being impossibly high. There's one tricky problem with this pipeline approach that's worth understanding. Sometimes an instruction depends on the result of the instruction right before it. Like, instruction 5 needs to know the result of instruction 4 before it can do anything. but instruction 5 is already being fetched and decoded before instruction 4 has finished executing. What does the CPU do? It guesses. Seriously. Modern CPUs have a piece of circuitry dedicated to predicting what the result of the current instruction will be, so the pipeline can keep moving forward based on that guess. And they're really good at guessing. Modern CPUs predict correctly over 95% of the time. When they get it right, the pipeline never stalls and everything stays fast. When they get it wrong, they have to go back and redo a few steps, which costs a tiny bit of time. This is called branch prediction, and it's one of those things that sounds like it shouldn't work but absolutely does. Let's make all of this concrete. Let's trace what actually happens inside your computer when it runs something super simple. Let's say you have a calculator app open, and you type 5 plus 3 equals. What actually happens? Step 1. The app sends that request to the CPU as a series of very simple instructions. Put the number 5 somewhere, I can work with it. Put the number 3 somewhere, I can work with it. Add those two things together. Send the result back. Step 2. The control unit fetches the first instruction. Put 5 in register 1. It decodes it, this is a load instruction. It executes it, the number 5 lands in register 1. Step 3, same thing for 3. The number 3 lands in register 2. Step 4, the control unit fetches the instruction, add register 1 and register 2, put the result in register 3. The ALU gets to work. It takes the value in register 1, that's 5, and the value in register 2, that's 3, runs them through the addition circuitry built from logic gates, and puts 8 in register 3. Step 5, the result, 8, gets sent back to the app, which displays it on screen. The whole thing happens in nanoseconds. A nanosecond is 1/billionth of a second. For something your brain processes as 5 plus 3, the CPU completed 4 separate operations, each going through its own fetch, decode, execute cycle. When you actually use a computer, it's doing this millions of times a second for every little thing on screen. Let me leave you with something that puts all of this in perspective. In 1971, about 50 years ago, Intel made the world's first commercially sold processor. It was called the 4004. It had 2,300 transistors. That's 2,300 tiny switches. It ran at the equivalent of less than 1 million clock pulses per second. Today, Apple's latest chip has 28 billion transistors. And it runs at billions of pulses per second. 2,300 transistors to 28 billion in 50 years. That's like going from a bicycle to a spaceship. And here's the beautiful part. The fundamental idea hasn't changed. It's still switches. Still on and off. Still ones and zeros. Still an OR and not gates. Still an ALU, registers, and a control unit doing fetch-decode-execute. The idea is exactly the same. We just got really, really good at making it incredibly small and incredibly fast. Okay, let's bring everything together. At the very bottom, a computer is made of tiny switches, transistors, each one either on or off. 1 or 0. Those switches are combined into logic gates, and OR, not, which implement simple rules about those on-off signals. Logic gates are combined into circuits that can add numbers, compare values, and make decisions. Inside the CPU, there are 3 main parts. The ALU is the calculator, it does all the math and comparisons. The registers are the notepad, tiny, ultra-fast storage right next to the ALU. And the control unit is the manager, it runs the fetch-decode-execute cycle and tells everything what to do. Clock speed tells you how many times per second the CPU pulses. More pulses, more work done. But faster means hotter. Pipelining lets the CPU work on multiple instructions at the same time, like a laundromat handling several loads at once. And all of this, billions of tiny switches, working in perfect coordination, runs your apps, your games, your browser, and everything else you do on a computer. Next time, we're going to look at memory in detail. How does RAM actually work? What's the difference between RAM and cache? Why does your computer slow down when you have too many tabs open? Subscribe so you catch that one. And if something in this video finally clicked for you, drop a comment, I'd love to hear it. I read every single one. See you in the next one.